Chapter 10, Section 3, Taylor's Theorem. Day 2. Page 504. Exercise 10. The function x squared over 1 minus 2x. The directions are to find the Maclaurin series for this function. And that is the same as the Taylor series for x near 0. There are 3 ways to do this problem. 3 ways. The first method is what we did on day 1, where we find the derivatives of this function, first, second, third, etc., and evaluate the function and its derivative at 0. Maclaurin series is at x equals 0. And then plug the results into the general form for any function of 0 plus f prime of 0 times x to the first over 1 factorial plus f double prime of 0 times x to the second over 2 factorial, and so on. Same thing with 3s and 4s. That's one way. Another method is to perform long division. This second method does not work for all functions. This one is kind of like a trick. We're going to do what we did in pre-calculus. Divide, multiply, change the signs, and add. Divide, multiply, change the signs, add. Divide, the word divide means what do I multiply to the first term? It's out here to get the first term in here. And that's x squared. Then multiply means multiply is what I just wrote times everything out here. X squared times 1 minus 2x is x squared minus 2x cubed. Change the signs. This becomes negative and this becomes positive. Add. First column 0. Next column is 0 plus 2x cubed, which is 2x cubed. We change the signs and then we start over. What do I multiply by 1 to get 2x cubed? 2x cubed. Multiply 2x cubed times all this. We get 2x cubed minus 4x squared. Change the signs. Add. Start over. What do I multiply by 1 to get 4x to the 4th? It would be 4x to the 4th. 4x to the 4th times everything out here is 4x to the 4th minus 2x to the 3rd. Change the signs. Add. And this continues forever. In general, each of these terms is 2 raised to the nth power times x raised to the n plus 2. The answer to this exercise is right here. Dot between these plus signs, these dots outside its end here, meaning there is no end. As soon as the end is in front, because when n is 0, that's when you get this first term. Because the 0 is 1, so let's just say 1 times x over 0 plus 2. In other words, 1 times x squared. So another way to write the answer would be sigma 2 to the n times f is to the n plus 2. So the n actually would have to start at 0 in order to see this first term here and go forever. And if it's 0, then 1 is 2 and 3. Notice when n is 3, that's to the third, which is 8. Times x to the 5th, which would be the next term. That's the ones that are written. So what's in the red circle is also the correct answer to number 6. What's in the green is correct. And red is another way to write it. And another thing you can do with this series, you can do in one step. Subtract 1 from each of these exponents. Make it 2 to the n minus 1, x to the n plus 1. But then we Instead of starting at 0, the n would start at 1, and then go to 2, 3, 4, 0, 1. See, this also generates the exact same terms that are inside the green. Alright, so we got these answers by performing long division. Another way to do number 10, because I said there's 3 ways, is to recognize that the given function is in the form a over 1 minus r. It's in the form, this closed form of the function is in the form a over 1 minus r. In that form, I mean anything on top, any term, and a 1 minus on the bottom. If the function is in that specific form, so we need 1 minus on the bottom, then you can say a is that, and r is what's after the minus sign. And from pre-calculus, you know, this is the sum, a over 1 minus r is the sum of a times r to the n minus 1, where n does start at 1 and go to infinity. This actually is in pre-calculus. So we can get the answer by saying right here where it says a, I'm going to put x squared. Next to a, I'm going to put what r is, which in this example would be 2x. R is what's after the minus sign, not including the minus sign. And the n minus 1 is the exponent on that. That's a. That's it right there. A r to the n minus 1. The n has to start at 1 and go to infinity. So we would call this a correct answer. Right here, I'll put yellow around it. Other ways to write that. I'll come over here. I got x squared. Since this 2x is to the n minus 1, I can say it's 2 is raised to the n minus 1, and next to it, x raised to the n minus 1. This whole thing is to the n minus 1, that means the 2 and the x are both. So then, since this base and this base are the same, we can multiply them, x to an exponent times the same base to an exponent. We would say keep the base and add the exponents. This exponent plus this exponent is n. The 2 to the n minus 1 just gets brought down. Sigma n equals 1 to infinity. That might even look different. Let's see what happens if we replace n with 1. We have 0 here, 2 to 0 is 1. Oh, here's a mistake. This x squared should be there. When you add the exponents, 2 plus n minus 1 is n plus 1. So that's the same exact thing, I believe, that we got previously. Took a dual page. These are matching exactly. And you could also see this is geometric. A over 1 minus r means geometric, because here's a term, and if you multiply any term by the common ratio, that's how you get the next term. X squared times 2x is 2x cubed. 2x cubed times the common ratio is 4x to the 4th, etc. So that's number 10. And now we're going to do number 22. page 504. We have this function, which is the square root of 1 plus x. The derivative of that function is 1/2 times 1 plus x to the negative 1/2. The function given, evaluated at 0, is 1. The first derivative evaluated at 0, because anything to the 1 plus 0 is 1. 1 to any exponent is 1. 1 times a half is a half. So the function, any function, can be approximated by a Taylor polynomial of whatever degree I want. Let's say I want degree 1, which is f of 0 plus f prime of 0 times x. It's just the very beginning of what we were talking about here. If we only go to x to the first power, it's a Taylor polynomial of degree 1, but it's also called the linearization, because this will be the equation of a line. So the function, the square root of 1 plus x, can be approximated by f of 0, which is 1, plus the derivative at 0, which is a half, times x. So the question says this approximation is used when x is small. Estimate the maximum error when the absolute value of x is less than 0.01. That's the question. On a sheet that you have that's called Taylor's Theorem, there's a formula for the error, and it looks like this. When a Taylor polynomial is used to approximate a function, the error will be less than or equal to max absolute value n plus first derivative evaluated at x. It really says minus c, but c is 0 in this case because x is near 0, divided by n plus 1 factorial times the maximum x. Actually, the absolute value of the maximum x, raised to the n plus 1 power. So you have this formula on a handout. What it means is, if we found a polynomial by going up to the first derivative, to find the error, this means go to the next derivative. In this case, the second derivative. Whatever derivative we went to get this polynomial, in this case, the first derivative. To find the error in the approximation, we go to the next derivative, find its maximum value, that's all that means, put it over n plus 1 factorial, and multiply that by the maximum x value, which will usually be in the question. The biggest x can possibly be, raised to the n plus 1. So notice the exponent is n plus 1 factorial down here, and this is the n plus first derivative. All right, so to answer this question, which is estimate the maximum error, we have to find the second derivative. In this case, in this problem, the second derivative is negative 1/4 times 1 plus x to the negative 1/2. I'm getting the second derivative from right there is the first derivative. And we actually need the absolute value of that. So we have to figure out what the biggest number this possibly could be. So what I did on a calculator is I actually looked at the graph of this, negative 1/4 times 1 plus x to the negative 1/2. Actually, I looked at the graph of the absolute value of -1/4 times 1 plus x to the -1/2. And I could see that it's a graph that going from -0.1 to 0.1, I mean -0.01 to +0.01, that's the interval in the question, but the graph in that window, -0.01 to 0.01, starts up and goes down. So the maximum is when at the end point here, which was when x was -0.01. So plugging that in, you get the biggest that can be. The biggest number is 0.2538. So to answer this question, we're trying to estimate the error in the Taylor polynomial that was given. It'll be less than or equal to. Biggest value that can be is 0.2538. And I put that over n plus 1. This is n plus 1. So 2 factorial goes in there. And the maximum x in this problem, x is always less than 0.01. So that's what I put in this box, in the green, 0.01. But it's raised to the n plus 1, which is 2. We found the second derivative, so that was 2 factorial, and that exponent is going to be a 2 also. So just calculate all that. 0.2538 divided by 2 factorial times 0.01 squared. And I got 1.269 times 10 to the -5th. And that's what we'll take as our answer. Answering the question, maximum error in this polynomial, which is actually a line, the graph of that would be a line, is used to approximate this, 1 plus the square root of x. The error in the approximation will be less than this, 1.269 times 10 to the -5. Provided x is between -0.01 and +0.01. All right, so next one we're looking at is number 32. It says f of x equals 1 plus x raised to the k. But if you continue reading, it says k is 3, so I'm going to put that in right away. Use the Taylor polynomial of order 2, Taylor polynomial of order 2, to find the quadratic approximation of this function at x equals 0. Since it says Taylor polynomial at x equals 0, we could also say it's a Maclaurin polynomial, or part of a Maclaurin series. So first we'll do that, and then we'll read the rest of the directions. The derivative of this function is 3 times 1 plus x to the second times the derivative of what's in the parentheses. The second derivative is going to be 6 times 1 plus x to the first power. The function evaluated at 0 is 1. The first derivative evaluated at 0 is 3. And the second derivative evaluated at 0 is 6. So from this we got that, from this we got that, from this we got that. 1 plus x raised to the third power can be approximated with a polynomial of degree 2, Taylor polynomial. And the polynomial of degree 2 means f of 0 plus f prime of 0 times x to the first over 1 factorial plus the second derivative evaluated at 0 times x to the second over 2 factorial. So 1 plus x to the third can be approximated by the polynomial 1 plus 3x plus 6 over 2 factorial times x squared. Because f prime of 0 is 3, and f double prime of 0 is 6. 1 plus x to the third can be approximated by the polynomial 1 plus 3x plus 3x squared. Because 2 factorial is 2. Now the directions are if x is between 0 and 1, x is between 0 and 1, for what values of x in that interval will the magnitude of the error be less than 1/100th? So the question is, for what values of x will the error be less than 1/100th? So the error is always, look at your formula, it's the maximum of the absolute value of the n plus first derivative. So what derivative did we go up to get this polynomial? We went up to the second derivative. So the next one would be the third. We need the maximum value of the third derivative of the function. We need the biggest value of that over 3 factorial times the maximum x, the absolute value of that, raised to the third. So these are all 3's, third derivative, 3 factorial, exponent 3, because we went up to the second derivative, we went to the second derivative to get this polynomial. So we use the next derivative, the next term, with all these 3's to get the error. And the directions we want this error to be less than 1/100th. Well, to finish this, we need the third derivative. We have the first and second. The third derivative of this function is going to be just 6. Since the second derivative was 6 times 1 plus x, the derivative of that is just 6. Well, this is easy. The biggest this ever is 6. So right there, all that gobbledygook, you just put a 6 there. 3 factorial gets copied. The x is what we're trying to find. So read the question. It says, for what values of x? I mean, we don't know the value of x that we would put there. This exponent gets copied. So we do. So there's your error. And we need the error to be less than 0.01, 1/100th. Well, 6 over 3 factorial is actually 1. 1 times x cubed has to be less than 0.01. So we should use absolute value there. So if we take the cube root of 0.01, we get 0.215. So we'll say as long as the absolute value of x is less than 0.215, the error in this polynomial approximation will be less than 1/100th. Just checking on the cube root. The cube root of 0.01 is about 0.215. So that's that one. Let's look at number 34. F of x equals 1 over 1 minus x. Point out that that's the same as 1 times 1 minus x to the negative 1. Same thing. Use the Taylor polynomial of order 3 to find the cubic approximation at x equals 0. So to find the cubic, the polynomial of order 3, we need to go up to the third derivative. The first derivative is negative 1 times 1 minus x to the negative 2 times the derivative of what's in the parentheses. So it ends up being positive 1 times 1 minus x to the negative 2. The second derivative is coming from here. Is going to be negative 2 times 1 minus x to the negative 3 times the derivative of what's in the parentheses. That becomes positive 2 times 1 minus x to the negative 3. The third derivative coming from this is going to be negative 6 times 1 minus x to the negative 4 times the derivative of what's in the parentheses. That becomes positive 6 times 1 minus x to the negative 4. Well, we only need up to the third derivative to get the polynomial of order 3. But to answer the question coming later, which is given upper bound of the magnitude of the approximation error, the error is going to require the next derivative, which would be the fourth derivative. Coming from this would be negative 24 times 1 minus x to the negative 5 times the derivative of what's in the parentheses. So it's positive 24 over 1 minus x raised to the positive 5. Well, I would like to point out that this is that special case where it's in the form of a over 1 minus r. It's in that form, a over 1 minus r, which means it's geometric, a over 1 minus r, where a, the first term is that, r is what's after the minus sign. So in this case, since r is x, that means that's what I multiply to the first term to get the next term. 1 times x is x. And if I multiply this term by r, I get the next term. If I multiply the term I just wrote by r, the common ratio, I get the next term. So there's a quick way to get the series in this case. The function 1 over 1 minus x can be approximated with a Taylor polynomial of order 3. In other words, 1 over 1 minus x can be approximated with this polynomial. 1 plus x squared plus x cubed. Up here I wrote a series, here I wrote the Taylor polynomial of order 3 at x equals 0. Now the question is, what is an upper bound for the magnitude of the approximation error? The error is less than or equal to the maximum value of the absolute value. We went up to third derivative to get this order 3 polynomial, so we're going to say we need the maximum value of the fourth derivative of the function over 4 factorial times the maximum x to the fourth power. So 4, 4, 4. The fourth derivative was over here in this red circle. So I'm trying to think of the biggest that could possibly be. that's going to be when x is 0.1. Because in the directions it says the absolute value of x is less than or equal to 0.1. So if I put that biggest x value in here, in this red circle, 24 over 1 minus 0.1 raised to the fifth. I get 40.644. That's what would go in this spot. But why don't I just divide that by 4 factorial before I write anything down? Divided by 4 factorial. So doing all that, I got 1.6935, etc. And I have to multiply that by the biggest x, which is given. X is less than 0.1. So put times 0.1 raised to the fourth here. So that comes out to be 1.6935 times 10 to the negative 4. So I just want to remind you that what I did to get this 1.6935, I found the fourth derivative in this red circle. I figured the biggest that could be by putting 0.1 in place of x. And whatever I got there, I divided by 4 factorial. That's how I got the 1.6935. In place of max x, I put 0.1. So that's why it's x times 0.1 to the fourth.